All right, welcome to Math466 Advanced Applied Analysis. This is lecture 6. And what we're going to do today is we're going to continue our stuff on Fejer series and Dirichlet series. So we've started with the Fejer kernels and the Dirichlet kernels. I'm not sure. No, it doesn't even let me walk over this far. Well, now it does. All right. So let's see if it can walk over far enough here. Okay. Oh, wow. Wow. Interesting. All right. So it's able to, oh, this is good to know. It's able to walk all the way over here. So here is the Dirichlet series. Here's the Fejer series. And if Karan moves forward, we can see his nose. All right. And so we talked a little bit about why one is better than the other. And the reason the Fejer series is much better than the Dirichlet is that the Fejer kernel is an approximation to the identity. The Dirichlet kernel is not. And we showed that if we integrate it against the Dirichlet kernel, we get the Fourier series. If we integrate against the Fejer kernel, we get a weighted Fourier series. And the weights, it's not a huge difference. And one of the things you learn as you go further and further in mathematics is smooth weights often simplify the analysis enormously. Sharp cutoffs are painful. So if you look at what's going on with the Fourier series, you sum the Fourier coefficients from minus n to n. So that means you have 100%, 100%, 100%, 100%, 100%, 100%, 100%, 0. It's a sharp cutoff as to what you have. With the weighted Fourier series, the weight of the coefficient n is big N minus little n absolute value over big N. So the weight starts off at 100% and then goes down linearly to 0. And that nice linear change is going to turn out to lead to a lot of nicer properties. It means that the Fejer kernel is giving us an approximation to the identity. If you look at these formulas, which come essentially from applying results in geometric series, strongly urge you to do the calculations. We saw why this is looking like an approximation to the identity. It's non-negative. Each one of these dn's integrates to 1. Since we have n of them and divide by 1 over n, we get something that integrates to 1. If x is very close to 0, this looks like 1 over big N. I'm sorry, it looks like n squared over n, so it looks like n. So it's blowing up at x equals 0. And as x is a fixed distance away from the origin, then you have a big N down below, and the top will be bounded by something nice. Because, sine squared is bounded. It can't get too large. Okay. What's going on now? So how do we prove, the big theorem is if you have an approximation to identity and you have a continuous function that's periodic on 0, 1, then f convolved with your series converges pointwise to your function. So it's basically the best type of convergence you can have. The series converges at each point. So the question is, do we need to prove this for the Fejer series, specifically using properties of the Fejer series, or can we just prove this for a general approximation to the identity? When do we need to use the actual properties of something? How many of you have taken abstract algebra? All right, let the record show my hand is not raised. I have not taken abstract algebra, though I have taught it twice. There's a great result that E and pi are transcendental. This means they are not the roots of a polynomial of finite degree with integer coefficients. And we have the following theorem. E times pi or E plus pi is transcendental. We believe both are transcendental, but we can prove that at least one of them is. Has anybody seen this theorem? You've seen it? Okay, have you seen it?
Sorry, can you just say again what transcendental?
So we say alpha is algebraic if there exists a polynomial of finite degree and integer coefficients such that f of alpha equals 0. So this means there's no finite polynomial with integer coefficients that evaluates to 0 at pi or e. But square root of 2, the polynomial x squared minus 2. I, the polynomial x squared plus 1. So if you're not transcendental, you're algebraic. And the great result is that at least one of those two is transcendental. Does anybody know any facts about e and pi that might be useful in the proof? Any relations between e and pi that might help? can't remember if we've done this in this class or in complex. This is the painful part of my year.
You're thinking of like e to the I.
Yeah. E to the I pi equals -1. Does this seem like this could be useful in the proof because it connects E and pi? Yes. Has absolutely nothing to do with the proof. This is actually a general statement. If alpha and beta are transcendental, then either alpha beta or alpha plus beta is transcendental. The proof does not need anything about them. I will just quickly sketch the proof, and then we'll prove what we actually care about for this class. So assume both algebraic. So this is a proof by contradiction. So alpha plus beta is the root of a polynomial of finite degree. With a little bit of work, you can show alpha plus beta squared is the root of polynomial of finite degree. And with a little bit of work, you can show if you have two algebraic numbers, their sum is algebraic, their difference is algebraic, their product is algebraic. So this is also algebraic. But this is equal to alpha minus beta squared. So alpha minus beta squared is algebraic. If a number is algebraic, so is its square root. So alpha minus beta is algebraic, but alpha plus beta is algebraic. And now if you add or subtract, this gives you 2 alpha and 2 beta are algebraic. Well, if twice of a number is a root, then you can just multiply by appropriate powers of 2, and you'll get alpha and beta are algebraic, and that's a contradiction. So what's really going on here, it's a general statement. The details don't really matter for what we're doing. We're not really doing stuff on transcendental numbers. It's just a nice result to see. That when you first hear the result, you might think it's going to depend crucially on properties of E and pi and how they're related. All that matters is that E and pi are two transcendental numbers. When we see the Fejer theorem, that the Fejer series converges pointwise if f is continuous and periodic, the questions you ask is, how am I going to prove this? Do I need to roll up my sleeves and use properties of the Fejer kernel? What properties of the Fejer kernel do I need to use? Do I need to use the explicit formula that it's sine squared n pi x over n sine squared pi x? Or do I need just something weaker, that the Fejer kernel has these three nice properties and is an approximation to the identity? When you're trying to prove results, it's always a question of how general is your result? How specific is it to what you're studying? And here, we actually do not need that many properties of the Fejer series. Okay? So now let's prove the main result. So theorem, f is continuous, periodic. We'll let Tnf of x be f star with the Fejer series at x, which is the integral, let's do -1/2 to 1/2 of f of y fn x minus y dy. Then the limit as n goes to infinity of Tnf of x equals f of x. So we have pointwise convergence. You could ask, but I'm not going to, how does the convergence depend on the point x? Is it uniformly converging? I will leave that as something for you to ponder. I'm just happy that we have pointwise convergence. That's the most important property you could have for a series, that at each point, it's going to the right value. Okay, proof. Well, it seems to make sense to look at Tnf of x minus f of x. Right? Let's show that this is going to 0. Well, Tn of f, this is going to be the integral from minus a half to a half of f of y, fn of x minus y, dy minus f of x. How do I want to write minus f of x? I want to somehow look at this difference. So this first one is an integral of f of y, fn of x minus y, and then I'm subtracting just f of x. So what are the two things I love to do in a math class? Now, I love to take logs. Well, I can't really take logs because I just have one item here. What else do I love to do? You've all had classes with me. Algebraically, what do I like to do to an expression? To try to simplify it, to try to attack it. Add 0 or multiply by 1. So it's either add 0 or multiply by 1. Since I have an f of x, and I want to somehow combine it with this, I probably want to multiply by 1. What's a good way to multiply f of x by 1? What do we know that equals 1? I'm sorry? Be more specific. You said the Dirichlet?
Or not the DN.
Well, we're working with the Fejer kernel right now, so we shouldn't really be looking at the Dirichlet kernel. So what related to the Fejer kernel is 1? It has 3 properties. What property of the Fejer kernel gives us 1? You're close. I'm sorry? So the approximation identity gives us 3 things. It's non-negative. What's the next thing? Not that it equals 1. The integral equals 1. So I can write this as minus f of x, and the integral from minus a half to a half of fn of, say, y dy. Right? And so I've just subtracted 1. I mean, I've just multiplied by 1. I can move the f of x inside. So what I'm going to do is I'm going to rewrite this. This first piece is minus a half to a half. I'll write this as f of x minus y, fn of y dy, minus the integral from minus a half to a half of f of x, fn of y dy. I'm going to write this, just basically change variables. This way both of them have an fn of y. And now I can subtract very nicely. And so it's all about trying to do the algebra in a nice way. So I now get the integral from minus a half to a half f of x minus y minus f of x times fn of y dy. And I want to show that this goes to 0. Okay? So which values of y are easy to understand the integrand? Yeah, if y equals 0, it's a pretty easy integrand. It's just 0. What if y is very small? What can you tell me about the integrand?
It has to be small because if you're assuming f is continuous,
Mm-hmm.
then you can bound f x minus y minus f of x, assuming y, if you bound y.
Okay, so if y is really small, then this part over here is going to be really small. So we're going to split the integral up into 2 parts. We'll split it, the integral from minus delta to delta of f of x minus y minus f of y, fn of y dy, plus the integral from, I'll just write it as x greater than delta, because we know we're in the interval minus a half half, of f of x minus y minus f of x, fn of y dy. So we have 2 pieces. We expect this piece to be small because y is close to x. What about this piece? So what are the properties do we have of an approximation to the identity? It's non-negative, it integrates to 1. What's the third property? It's not 0. The integral, if you're a fixed distance away from 0, is arbitrarily small. So given any delta, there is an n naught such that for all n greater than n naught, this is less than delta. So if I didn't have the difference of the f's here, if I just had little f's, if I just had the integral of the kernel, then I know that this would be small because I'm staying a fixed distance away from the origin. Okay, how large can f of x minus y minus f of x be? Could that get arbitrarily large? What do we know about f of x minus y minus f of x? How large could it be? Could it be infinitely large? Could this be blowing up? What do we know about f? What are we assuming about f? F is periodic. We need more than just f is periodic. So we're assuming f is also continuous. So if you know you have a continuous function on minus a half a half, what do you know about a continuous function on minus a half a half? It takes a maximum value. So if it takes a maximum value, it also takes a minimum value. The function is bounded. So what can you tell me about this difference? It's bounded. So in absolute value, let's look at the absolute value. This will be less than or equal to twice the maximum of f of, we'll call it f u, right? Times the integral over x greater than delta of the absolute value of fn of y dy. Right? I'm just taking the absolute value of this expression as a bound. The absolute value of this difference is going to be at most twice the maximum value, which is fixed. What do we know about the absolute value of fn of y? So what do you know about the absolute value of fn of y? Because I'm sorry? We don't want to use the stuff on the board. We don't want to use specific properties of the Fejer kernel. We want to do a proof for a general approximation to the identity. We know that the integral of f, if x is greater than delta and absolute value is small. We have the integral of the absolute value of f. Is it painful for us that we have the absolute value? Okay, why not?
Well, I think because isn't there the absolute value convergence test that says that?
Nope, not quite.
Isn't it supposed to be greater than 0?
Yeah, the function is greater than or equal to 0. So what's the relation between the absolute value of f and f? They're equal. So now we use the third property because as the absolute value of fn equals fn, it's now small. So we're using all three properties of an approximation to the identity to show that this, we put in this piece because it integrates to 1. We then use the fact that it's non-negative, and we use the fact that it integrates to something arbitrarily small if you're a fixed distance away. So we can make this piece as small as we want. You give me an epsilon, I can choose an n naught, such as for all n greater than n naught, this is at most epsilon. Okay, so that handles that piece. What about this piece? How do we handle this piece being small? Well, f is continuous. So if we choose delta sufficiently small, we can make this at most epsilon. So now, we're bound the absolute value of this piece. Okay? For all epsilon, there exists a delta such that f of x minus y minus f of x is less than epsilon. What do I need about f for this statement to be true as written? Why does this hold?
Because f is continuous.
Okay. I need a little bit more than continuous.
Uniformly.
It's uniformly continuous. I'm on a closed interval. This delta is independent of x. What would be terrible is if we had to use a different delta for different places of x. But we can actually use the same delta everywhere because f is uniformly continuous. Delta is independent of x. F is uniformly continuous, therefore delta is independent of x. So we can make this less than or equal to epsilon, and so this integral here is going to be less than or equal to epsilon, the integral from minus delta to delta of the absolute value of fn of y dy. Well, we already know that the absolute value of fn is just fn, right? So I can drop the absolute signs. So all we have to do is show that this integral can't be too large. How do we know that this integral isn't too large?
It's less than 1.
Good. Why is it less than 1? Well, it's not quite less than 1. Less than or equal to 1. Why? Not the identity. F is an approximation to the identity. So because Fn is approximation to the identity, what do we know? It integrates to 1 over the whole range. We're integrating over a subrange, and the function is non-negative. So because the function is non-negative, this is the same as it's less than or equal to epsilon, the integral from minus a half to a half of fn of y dy, which is just equal to epsilon times 1. And so that shows that this term goes to 0, this term goes to 0, the difference goes to 0. This finishes the proof. So we've just shown that an approximation to the identity converges to, when we use that kernel, gives you pointwise convergence. What makes this so useful is that for the Fejer kernel, we get a weighted Fourier series. I can put in any approximation to the identity. I could put in a Gaussian with variance going to 0, like in J's talk. Oh, no, I'm sorry, J's variance 1 to infinity, so the opposite of J's talk. But I wouldn't be able to do the integrals in nice closed form. I wouldn't be able to express them in terms of a sum of things I care about. By using the Fejer kernel, we actually get a weighted Fourier series. And we do not have to open up our sleeves and use specific properties of the Fejer kernel. We just need to use that as an approximation to the identity. So the question is, what goes wrong for the Dirichlet kernel? Where does this proof break down for the Dirichlet kernel? What step is not valid? Because we could do a lot of the arguments very similarly. Do you see?
Non-negative.
Non-negative. That's where things break down. So when we put in the absolute value here, we want to then basically say that the integral of the absolute value is small. We know that the integral of the function is small. So for the Dirichlet kernel, we know that the integral of the Dirichlet kernel is 1. But the Dirichlet kernel is highly oscillatory. Imagine I give you $1 million, then you give me $1 million, and I give you $1 million, then you give me $1 million, and let's do this an even number of times. At the end of the day, how much do you have from me? I'm sorry.
Very large sum.
I give you $1 million, then you give me $1 million.
How much net?
Net. Net is 0.
Yeah.
So your net is 0, but you have some very high fluctuations where you have moments in time when you have $1 million. So the problem is the Dirichlet kernel is it's not non-negative. It's both positive and negative, and if you integrate the absolute value of the Dirichlet kernel, it's really bad. If you look at the Dirichlet kernel now, you have the sine of 2n plus 1 pi x over the sine of pi x. And so you can try to figure out what would be the integral of that. So what's the integral of the absolute value of that? And it turns out it's quite bad. That's where things break down. That's why it's so much harder to work with the Dirichlet series, because I can't just drop the absolute values. If you have something that's non-negative, absolute values are not a problem. The absolute value of a sum is the sum of the absolute values, if everything is non-negative. Okay, any questions on this proof? So this is a beautiful result. You can actually use Fejer's theorem to prove a lot of other things. Okay, we're happy with this? All right, the next part then becomes Dirichlet's theorem. What if we now use the Dirichlet kernel? What can we get? So let's have f is continuous, periodic, and differentiable at x naught. Then Sn of f at x naught, which is f star the Dirichlet kernel at x naught, converges to f of x naught. It is not the case that the Fourier series converges pointwise for all functions. If the functions have discontinuities, it makes sense that you should have some issues. So for instance, imagine I give you a function defined like this. I hope to have good convergence here. I hope to have good convergence here. But I have a discontinuity here. If life was good, what should it converge to at the discontinuity?
The center of the 2 points.
I'm sorry? Yeah, the center of the 2 points. And it turns out what happens for a lot of functions is it's called the Gibbs overshoot. It actually goes down, comes up, and goes down like this, and misses by like about 18%. So there's a nice exercise in the book about this. But we have some issues at places where it's discontinuous. The more differentiable the function is, the more derivatives that exist, the more we can show. Okay. So now we're going to assume a slightly stronger condition than before. We're assuming differentiability just at the point x naught. So we are not assuming that the function is differentiable everywhere. Of course, if the function is differentiable everywhere, then you could just apply this argument at every single point. Before, we used uniform continuity of the function. Well, everything we're doing now is focused on one point. And so all I care about is what's going on in one small little area. Okay? So now what we want to do is we want to prove this. And the proof should be fairly similar. Okay. So let's look at there's 2 ways to subtract. I don't remember which way I did it in the book. So let's look at Fn of x naught minus f of x naught. And we'll do the same trick as before. We'll write this as the integral from minus a half to a half of f of x minus y dn of y, I'm sorry, x naught, minus f of x naught dn of y dy. The first part is just what it means to be taking the convolution. And we showed last class that that just turns out to be the Fourier series from minus n to n. All right, so this is looking a lot like what we did before, integral from minus a half to a half. Well, let's break it up into 2 parts. We'll do absolute value of y is less than, I just realized I was writing absolute value of x greater than delta should be absolute value of y greater than delta. Absolute value of y less than delta, f of x naught minus y minus f of x naught dn of y dy plus the integral absolute value of y greater than equal to delta f of x naught minus y minus f of x naught dn of y dy. So we have 2 pieces to study just as before. We have the places where y is close to x, y is close to 0, so that these two functions are close to each other. And we have when y is a good distance, a fixed distance, so there's a real separation here. We can't just take absolute values. Why can't we take absolute values? So what would go wrong if we just take absolute values? So if we go back to the situation, I give you $1 million, you give me $1 million, I give you $1 million, you give me $1 million. Let's bound how much money you have by taking absolute values of each transaction. $1 million plus $1 million plus $1 million plus $1 million plus $1 million. We will bound how much money you have by a large multiple of $1 million. Trust me, I don't like you guys that much. I'm not going to be giving you large multiples of millions of dollars. Why is it such a bad bound? Because you lose cancellation. So whenever you take absolute values, if your function is highly oscillatory, it's a bad idea to take absolute values. This is why I want to go slowly through these proofs. This is why I want you to read the stuff at home beforehand. I want to emphasize the key ideas so you have the techniques as to how you do this. I can go through these proofs much faster. If you want, as a challenge, we can see how long would it actually take us to do one of the chapters in the book. Okay, I'm seeing head shakes like this. I really want to emphasize why we're doing what we're doing, why these proofs work. If your function is highly oscillatory, as soon as you take an absolute value, your bound is terrible because you lose all the cancellation. So it is deadly for us. It would be disastrous for us to take an absolute value here. What do you think we're going to need to use? Okay, probably we need to use the derivative because I'm telling you the function is differentiable. So where do you think a derivative is lurking? Where do you almost see a derivative? Yeah, so I saw both of you pointing. Where's the derivative?
If you divide it by the changes.
Yeah, if I divide this by y and multiply by y, that's going to look like a derivative. So maybe I can attack that one by doing a derivative. So we'll break it up into two parts. We'll deal with this part first, then we'll deal with that part. And again, when you have conditions, the conditions can often help guide you in terms of what you should be doing. So we'll look at the first part. So we have the integral y less or equal to delta f of x naught minus y minus f of x naught over y. And then what else should I be using? Not just the derivative, but what else do you think I should be using at this point in my proof?
It's continuous.
That's continuous. Periodic. There's something else we might need to use. So the previous proof I tried to do it in as much generality as possible for all approximations to the identity. Do we have an approximation to the identity? No. What do we have? We have the Dirichlet kernel. This proof is, at some point, we're going to need to use the fact that this is what the Dirichlet kernel is. So we will multiply by the sine of 2n plus 1 pi y over the sine of pi y. And since I multiplied by y down below, I got to multiply by y upstairs. Okay? Because my function is differentiable, as y goes to 0, is this well defined? Is this quotient well defined away from y equals 0? Yeah, Yeah, because if y is away from 0, my function f is continuous, and I don't have to worry about dividing by 0. This is just some nice function, g of x naught of y. Now what about we then have y over sine pi y, and we have the sine of 2n plus 1 pi y.
Can you say sine pi y is equal to pi y?
So if y is really close to 0, then this, I would probably want to put a pi over here and divide by a pi over here. So maybe I'll put a pi y and a pi y over here, and I'll call that whole thing my g of x naught. So this limit would be 1. This is going to be a nice function, but now I'm integrating this nice function times a highly oscillatory function. But g is bounded. This is bounded by 1. This will be at most delta. So I would be able to show that this integral is small. Let's look at what's going on down here. Once y is large, this difference could be large. And this is highly oscillatory. I can't take absolute values. So unfortunately, well, this is the natural thing to try. This fails miserably. We can't break it up like this. Because, well, we could show that this part is small. To then handle this part, I've got a strange function here. So, sadly, this has to be erased. And this is just an integral. Y goes from minus a half to a half. And so I come up over here, and I have to do this for all values of y. And so I integrate from minus a half to a half. I can still call this function g of x naught of y. And in fact, I can even expand it. Let me call this whole expression here some nice function. This is the integral from minus a half to a half. Let's call it phi sub x naught. Phi is a fun thing to write. Of y sine 2n plus 1 pi y. What kind of function is this? What kind of function is this? So what can you tell me about this function phi of x naught? It's g of x naught times pi y over sine pi y, or expanding out even further, it's like this. What do we know about f, and how does that knowledge of f propagate down to phi?
It's periodic.
So it's periodic. So f is periodic. Then we've got to be a little bit careful. I'm not quite convinced that this is periodic over here. So I'm not sure we have it's periodic. What do we know about f? What kind of function is f? Continuous. Is this new function continuous? Where's the only danger point? The only danger point is when y goes to 0. Well, when y goes to 0, because f is differentiable, this quotient exists. So this new function is continuous. Or at the very least, it's bounded. And so now, one way to view this is the imaginary part of the integral from minus a half to a half of phi of x naught of y e to the negative 2 pi. Be a little bit careful here. 2n plus 1 over 2 of y dy. Oh, so 2 pi I, sorry, 2 pi I. What does this look like? Where have we seen something like this before? It should look familiar. I've got a function, and I'm integrating against e to the negative 2 pi I something times y dy. We've defined this as the Fourier coefficients. Okay? If you are not seeing that this is a Fourier coefficient, you need to do a better job reading the chapter to prepare for class. You've got to recognize that this is taking a Fourier coefficient. Now what we've always done is we've taken the Fourier coefficients at integers. 2n plus 1 over 2 is not an integer, it's a half integer. What I might have to technically do is put in one of the exponentials and change my function ever so slightly. It's fine. So technically what you would then have is you would have a slightly different function here, so I now would have an ny. And I'm just incorporating a e to the negative pi I y into this. Now we use the Riemann-Lebesgue lemma, that the Fourier coefficients of a nice function tend to 0. So by the Riemann-Lebesgue lemma, this is a Fourier coefficient of a nice function. Therefore, goes to 0 as n goes to infinity. And that completes the proof. So we keep tweaking what our function is. And at the end of the day, we have a function where we're essentially just taking a very large Fourier coefficient. And the Riemann-Lebesgue tells us that the Fourier coefficients go to 0. So it's really worth analyzing what breaks down in the Fejer proof and why it doesn't work here. Because a lot of times when you are doing calculations, it's very easy to put in absolute values to bound things. And if you have oscillation, you lose all of that. That's what makes the Dirichlet series so much harder to work with. That's what makes the Fourier coefficients hard to work with as opposed to the weighted Fourier coefficients. The Fejer kernel gives us something that's non-negative. And that we can work with. And so from this point, we can't split this up as we did before because we now have a new function. And the Dirichlet series, if we try to put in absolute values, we're dead. We can't do the integration in general because we don't know what the function is. And we've got this new function which is some kind of ratio. It's horrible. We have no chance. So we have to go through a longer proof like this. And then what we do is we start going, well, let's look at what's going on. And now we're actually rolling up our sleeves and using the fact that this is the Dirichlet kernel. We're not proving this for an arbitrary function. We are proving it for a very specific choice. And for this choice, we then start to use its properties. We don't have nice properties that we have when it's an approximation to the identity. But we still have some properties. We have an explicit closed form expression. And the key part is that it's the sine of 2n plus 1 pi x over sine of pi x. And so this sign over here, when we multiply by 1 cleverly, we see this is looking like a derivative. This is looking like something that's bounded. Your y gets only up to plus or minus a half, so we don't have to worry about this being 0 again. And this new expression is going to be well behaved. When we now start looking at what's going on over here, we can look at this as the imaginary part of an exponential. It's not quite the Fourier coefficient because we had the n plus a half. So we just remove that and we just tweak our definition of this function. And now we're taking a Fourier coefficient, a very high Fourier coefficient. And the Fourier coefficients tend to 0. If the Fourier coefficients were not tending to 0, you would not want to try to do a Fourier series expansion. Because then you'd be having significant contributions far down the line. The hope is that the coefficients are getting smaller and smaller and smaller so that a finite sum does a really good job approximating things. So there's a lot of really good analysis in this today. And then what we'll do on Friday is we'll talk about some of the consequences of this. What do we know about convergence? If we knew that the function was, say, twice differentiable or 3 times differentiable, at what point do we get enough information to be happy? When does the Fourier series converge absolutely and not conditionally? So there's a lot of technical stuff to make these arguments work. But the real lesson from today is that for a lot of purposes, rather than looking at what you're told to look at, if you look at something closely related to it, it's much easier and gives you all that you need. So rather than looking at the Fourier series, if we look at the weighted Fourier series, we get so much better convergence properties. Is it hard to multiply the nth Fourier coefficient by big N minus absolute value of n over n? No. These are very easy weights to work with. And so from a computational perspective, the weighted Fourier series is nicer. We are just trained, we grow up with sharp cutoffs. Is there anybody who was 93% admitted to Williams College? Or given 72% of an offer at Goldman? Right? We do things binary. Yes, no, on, off, you're in, you're not, you're tenured, you're not. So we like sharp cutoffs. But from an analysis point of view, the big lesson is sharp cutoffs are very hard to work with analytically. Smooth cutoffs are nicer. All right, that is a good place to stop.